Hi, I'm Robert Rojas. In this video, I will demonstrate to you how to build the different Hidden Markov Model or HMM components. Sample computations using a super tiny corpus containing 10 sentences and our simple tag set will be presented. To understand how the Hidden Markov Model works, I encourage you to watch the next video in the same computer science lecture notes channel titled the Viterbi algorithm, which will be using the HMM components that we will be building in this demonstration video. Let's start now. A hidden Markov model, or HMM, allows us to talk about both observed events, like words that we see in the input, and hidden events, like part of speech tags, that we think of as causal factors in our probabilistic model. It has additional two components on top of the Markov chain components. The two additional components are as follows. One, the set of P possible observations or vocabulary, and two, the sequence of observation likelihoods, also called emission probabilities. It's expressing the probability of an observation O sub t being generated from a state I. To illustrate how HMM works, let us use a very simple tag set that is shown on the screen. We'll also use our super tiny corpus that is shown on the screen. Let us compute the transition probability matrix. Using our super tiny corpus, we will compute some partial results only. Let us start with the tags of the words that can be found in the corpus that start a sentence. If we check the sample corpus, the words that start the sentences belong to the three parts of speech items only. That is, det for determiner, like the, prn for pronoun, like he, and n for noun, like Christ, Jesus, Judas. Some of them appeared more than once, like the, Christ, and Jesus. Let us use the equation shown on the screen to compute the transition probability matrix. The equation states that the probability of the part of speech tag sub I given tag sub I minus 1 is just the count of tag sub I minus 1 followed by tag sub I divided by the count of tag sub I minus 1 or the previous tag. Let us assume that each sentence has the initial start marker and the final end marker. Then let us compute the probability of the tags appearing after the start marker. We have to note that our super tiny corpus has 10 assumed start markers. Let us compute the det tag for determiners following the start marker. Our corpus shows that there are 3 determiners that start some sentences. Since it is difficult to decipher the parse tree representation stored in our super tiny corpus, I am also showing the corresponding sentences in the screen to easily see that there are 3 determiners that start some sentences, as pointed to by the red arrows. So, the probability of the det tag following the start marker is 0.3. For a prn tag for pronouns following the start marker, we only have one as shown on the screen, as pointed to by the red arrow. Therefore, its probability is 0.1. As for the n tag for nouns, following the start marker, we have 6 of them as shown on the screen. So the probability is 0.6. These computed values are entered as values of row 1 of the transition probability matrix. Then let us compute the transition probability for the different parts of speech items that follow the determiners or det. This det tag appeared 12 times in our super tiny corpus. Please note that we treated the word many as a determiner. If we treat it as an adjective, the computation will be different from what will be shown in the screen. So the computation for the det tag is shown on the screen. The det tag was followed by an n tag for nouns 11 times. So its probability is 0.92. The corpus also shows that the det tag was also followed by the adj tag for adjective, but it appears only once. So its probability is 0.08. Please note that the adj tag for adjective is not included in the transition probability matrix that we can see in the screen, but in reality it is included in the actual matrix. For illustration purposes, it belongs to the ones represented by the ellipses in the shown illustration matrix. So the result of computing the probability of the det tag is as shown in the screen. Let us compute the transition probability for the different parts of speech items that follow the transitive verbs or VTR. This VTR tag appeared 5 times in our super tiny corpus. 4 of them are followed by the det tag, and the other one is followed by the prn tag. So the computation is as shown on the screen, and the updated matrix looks like the one shown in the screen. Let us compute the transition probability for the different parts of speech items that follow the pronouns or PRN. This PRN tag appeared twice in our super tiny corpus. The first one is followed by the VTR tag for transitive verbs, and the other one was followed by a period. Please note that we ignore the period and we use the end marker instead. So the computation result is as shown in the screen, and the updated matrix looks like the one shown in the screen. Let us compute the transition probability for the different parts of speech items that follow the nouns or N. This N tag appeared 19 times in our super tiny corpus. This N tag is 4 times followed by a transitive verb or BTR tag, and 7 times it is followed by a period. Please note that we ignore the other parts of speech items like linking verbs, intransitive verbs, and we use the end marker instead of period. So the computation is as shown in the screen, and the updated matrix looks like the one shown in the screen. As for the end marker item, no parts of speech item follows it. So the resulting partial transition probability matrix looks like the one shown in the screen. We can view this transition probability matrix in the form of a transition graph as shown in the screen. For easy reference, in the transition probability matrix, I numbered in subscript the different states from 1 to 6. Please note that the total probability of some states is not equal to 1 because some parts of speech items were excluded from the sample computation. The B emission probabilities, that is, the probability of word sub I given tag sub I, represent the probability given a tag that it will be associated with a given word. The maximum likelihood estimation or MLE of the emission probability is computed using the formula shown in the screen. The formula states that the probability of a word sub I given tag sub I is just the count of tag sub I associated with the word sub I divided by the count of all the tags sub I in the corpus. Let us compute the words associated with the N tag for nouns. Let us use our super tiny corpus shown in the screen. There are 19 N tags. The first set of computation is shown in the screen, then followed by the next set of computations, and finally, the last set of computations for N tags. The resulting graph is shown in the screen. The list is enclosed in the green box. Please note that the total probability is a little bit higher than 1 because of the rounding up of numbers. We can also let go of the rounding up of numbers, and the result will be a little bit lower than 1. But inside the computer's memory, it should total to 1. Let us compute the words associated with the VTR tag for transitive verbs, as can be found in our super tiny corpus shown in the screen. The computation is shown in the screen, and the resulting graph is also shown in the screen. Let us compute the words associated with the det tag for determiners, as can be found in our super tiny corpus shown in the screen. The computation is shown in the screen, then the resulting graph is also shown in the screen. Let us compute the words associated with the PRN tag for pronouns, as can be found in our super tiny corpus shown in the screen. The computation is shown in the screen, then the resulting graph is also shown in the screen. We have built the different HMM components already. The next step is to demonstrate how HMM really works using these different components that we have built. I encourage you to watch the next video in the same computer science lecture notes channel titled The Viterbi Algorithm, which will be using these HMM components that we have built in this demonstration video. In that video, I will be showing to you how to POS tag correctly a sentence using HMM, even if the sentence being tagged is not found exactly in the corpus containing the POS tag sentences. Thank you very much. I hope these lecture notes in audiovisual form have helped you in some way in understanding how to build the different hidden Markov model components in your computer science journey. Bye!